You know your first quiz is next week. We postponed your first quiz not from today to next week. So next Monday you will your first quiz. Make sure that you do your homework. And the examples I gave it to you in the class. I sent you an email about it. I hope you received that. Today we will be talking about the linear algebra part. Some things you already know, but as the point of numerical analysis, what can we say about the systems, matrices, determinants? What can we say about the singular ones? And we will talk about two iterations, Jacobi iteration and Gauss-Seidel, to be able to solve the systems of linear equations, not differential. So I will start recording. Actually, it started already. Okay, nice. Again, do you have any question? We will have your first midterm quiz next week, next Monday. You hear me, right?
Yes, teacher.
Okay, great. Great. So let me share my new lecture notes with you. We will be applying with MATLAB today also. I will not share this, I will share. Let me stop that. I will share my desktop. I will ask you to do the same thing for the next week. Or maybe we will not, we can do it only for the final. Let's see. Okay, let's start. As I told you last week, we talked about how can we find the root of a given function. If this function is nonlinear, if it has cosine, sine, exponential kind of functions, we cannot find the root easily. And we said that the first thing we should do is plot the function and see that what kind of roots you have. And after that, to be able to find the exact value of the root, we talked about 4 different methods, if you remember, right? Secant method, bisection method, Newton-Raphson method, and regular-Falsy method. And they were touching or reaching the root in different ways. Any question? Oh, no problem, Ece. And I said, I told you I will show you with the graph tablet next week, but I can do it maybe next week. Let me try right now. If my tablet is gonna work. So as I told you last week, we talked about how can we find the roots. Why this does not work? Okay, here you go, it's working now. Like we were looking for how can we find the x that makes our function 0. So we said that the first thing we should do is plot it. If you plot it, you will see that what will be the roots of this function. I am still trying to understand this thing. So as you can see, there are 3 roots for that one. Maybe it's more, but between this 0 and a, we can say that there are 3 roots. And by looking at this plot, you can understand what kind of function you have. And after that, to be able to find these functions, sometimes these functions can be so complicated, like cosine x plus sine x squared equals 0. And you want to find what kind of x's that can make this function 0. And for this kind of things, we were we talked about the 4 different methods, if you remember that. Let me open my previous lecture. And we talked about Newton-Raphson method. And we said that for the Newton-Raphson method, so the first one was Newton-Raphson, right? Can you see this? I just want to summarize because you have an exam next week. Can you see what I'm writing? Do you see it?
That's writing is Newton-Raphson.
Okay, yes, great. Yeah, please, give some feedback now and then so that I can understand you are following me. Okay. For the Newton-Raphson method, we said that we are approaching our root by tangent lines. Yes, we have a class. Some of your friends are asking. Let me see. Okay, anyways. So, as I told you, for the Newton-Raphson, we needed some starting point x0, and from that point, we were defining a linear line, right? And wherever this linear line was reaching to the x-axis, crossing the x-axis, this was our next point. And from this x1, we were defining again a linear line that touches to our f of x. This is our f of x. And this is our real root, x real. I am trying to reach this. I'm trying to find what is that value. And by starting with x0, I defined a linear line from there. And from x1, I'm defining another linear line there. Let's say this is x2. And by following these linear lines, you can reach to the xr. This was Newton-Raphson. And we said that the iteration for Newton-Raphson was xi plus 1 equals xi minus f of xi over the derivative of f of xi. You remember that, right? And I already provide you the MATLAB code for that one. You don't have to understand each of it. You already have the basic programming courses. You know what for loop, what while, what if is. Just make sure that you know how to run a program, you know how to plot a data. These kind of things I expect you to know it after this class, okay? And the second method was bisection method, if you remember that. And for the bisection method we were using, let me write here, I am trying to get used to that thing, I just have it today. Sorry, bisection method. And for the bisection method, it was using intermediate value theorem. And if you remember it, for finding the roots, we needed 2 values. And we need to make sure that our function has different signs between this a and b. So we were looking what is f of a. It is positive f of a. And we were looking what is f of b. It is negative And intermediate value theorem tells us that there is a root between A and B. This is our real root. And what we were doing, we were checking for the next one, for x2, you can say that, we were checking the middle point of A and B. And let's say this is C, where C is A plus B over 2. Okay? And check that f of A, f of C, which is positive, then update A with C. And you know that your root is right now between B and C. Okay? So as the first iteration, root is between A and B. And for the second iteration, root is between C and B, because C and A has the same sign. So I updated A to C. And as the third iteration, you are checking again D, which is B plus C over 2. And this will be, so what is going to be the middle of BC? It will be somewhere here, D. And check f of D. F of D is negative, and that's why you will update what? C or B. Root will be between C and D now. So we updated B this time, right? And in the same way, you will be finding, you will reach to XR like that. This was bisection method. And for as the third method, we talked about secant method. And for the second method, last year, because I asked students from you to plot these methods and differences, how they are approaching to the root, I asked from them. And that's why I'm trying to explain this to you right now. I will ask you to explain this to me, okay? XY, you can, plot it better way. And for second method, as you know, we needed again two starting point, x0 and let's say x1. And between this x0 and x1, you are defining the second line, right? This is x0, this is x1. And whenever the second line passes the x, and this is your xr, real. From here, we were using in the second the previous value. So the previous value is x1. So between x2 and x1, we are defining a second line. Let's say this is crossing the x-axis here. This is your x3, right? And between x3 and x2, now you will define a second line. And this is your x4, wherever this second line crosses. And between x4 and x3, you will do it and you will reach the real root by second lines. And the iteration for that one was xi plus 1 equals xi minus, this was coming from the equation of a second line. I already provided the notes with you. You can see in a better writings there. Yi. This was the iteration for the second method. Okay, remember that. And the last one was the regular falsi. And for the regular falsi method, it was kind of the, like bisection and secant method, combining with the bisection and secant method. What we were doing for that one, we were again starting with two starting point, x0 and x1. And just as the second method, we were defining the second line, but this time, and finding the where this line crosses the x-axis. This is your x real. But this time, you were checking the signs of these. So x1 has, f of x1 is negative. f of x0 is positive, and check that what is x2. X2 is negative, then update x1, which means that you are gonna be looking the second line from x2 to x0, this one. And wherever this cross, check the sign, and since this is still negative, define a second line with x3 and x0. It was like that. So these were the differences between 4 methods we talked about last weeks, 2 weeks actually. Okay, remember that, and how we implement these from the MATLAB. The codes are with you. Make sure that just watch the video and implement these codes. You have it already. Do you have any question? Okay, then. Let me continue with today's class. We will talk about linear algebra. You already know how to multiply a matrix with a vector. So this is our matrix, 2 by 2. This is our matrix, vector, 2 by 1, which is a column vector. And to be able to multiply these, the sizes are important. Since this is 2 by 2 and since this is 2 by 1, and the number of rows in this one should be equal to the number of columns of the second one. And since these are both 2, this can be multiplied. And for multiplication, this row should be multiplied with this column and element-wise. 1 times -1, 2 times 2, and add them. 3 times -1 plus 2 times 4, and add them, and you will get 2 by 1 column vector at the end. And to be able to multiply matrices, again, size important. 2 by 2, 2 by 2, you can easily multiply that. And again, rows by columns. The first row, first column, the first row, first column value. First row, second column, it will be the first row, second column value. And similarly, second row, first column, second row, second column. And element-wise, you need to multiply them and add them. And this is how you will find the result for the matrix multiplication. I believe you already passed the linear algebra. You already know how to multiply matrices each other, right? I hope you are saying yes. And now the MATLAB part. How can we define these vectors and matrices in MATLAB? Today we will be talking about that. Let's start by defining a matrix. Let's define a matrix. You should give a name to the matrix, and if you are defining a matrix, you need to use square bracket, and you need to define row by row. Whatever the first row elements, write in here 2, 5, 6, -1. Let's say we have 4 columns and 1, 2, 3, 4, and go to the next row. So this is gonna bring you to the next row, and for that one, 0, 0, -2, 4, and let's say enter. As you can see, this is your first row, this is your second row, this is your third row, and we have 3 by 4 matrix, and you can check that one by size A command. It will tell you this has 3 rows, 4 columns. Okay, easily you can find the size of your matrix, and you can define a vector in the same way, but you know that your vectors can be either row vector or column vector. For row vectors, it is easy, 2, 4, 5, 7, 8, for example. This is 1 by 5. And for getting the column vector, you can take the transpose of it, and you can have the column vector, or you can put semicolons between them. If you put semicolons, it will be all also going down, which means that you will have a column vector. And let's say you will multiply A with U. You will multiply this matrix with this vector. Can you do that? Size A, let me remind you what was the size of A, 3 by 4. Size of U is 5 by 1. So we said that the number of rows in this one should be equal to the number of columns of this one should be equal to the number of rows of this one. So this 4 should be equal to 5 in that one, which means that this has either 4 by 1 or this has either 3 by 5 to be able to multiply them. What is that? Let me see. Yes, we cannot multiply, that's true. And so let's define another one, U2 vector. And U2 vector should have what size? 4 by 1, right? So that I can multiply A with U2. Uh-oh. No. Why? Because this is 1 by 4, not 4 by 1, right? So make this one transpose and it will multiply to you. We understand that the size is important. Our size of A was 3 by 4 and our size of U2 is 1 by 4. But it should be 4 by 1. That's why I take the transpose of it and the result is 3 by 1 matrix. Remember that. So let me open that too. So our A was 3, what was that? 3 by 4? Yes, it was 3 by 4 and our U2 should be 4 by 1. These should be equal to each other and the result will be that size. This will be the result, 3 by 1 vector. Okay, remember that one. And this is the matrix multiplication one. And what else we can do? And once you are multiplying the matrices, also size important, and you know that the multiplication is not, order is important. You can, it's not associative, which means that let's define another one. It was 3 by 4. Let's define 4 by 3 this time. 4 of 3. 1, 2, 3, and 5, 8, 0, and 2, 2, 2, and 9, 7, 1, let's say. And the size of B is 4 by 3. If I multiply with A and B, I will get 3 by 3 matrix. Remember that A is 3 by 4, B is 4 by 3, and the multiplication of them, these are equal to each other, which means that I can multiply them, and the result will be 3 by 3. This is true. And can I multiply B times A? I have the result. This is working. Can I multiply B times A? B is 4 by 3. A is 3 by 4. Sorry, A is 3 by 4. Yeah, B is 4 by 3. Can I multiply that? Emily? Yes, we can. What will be the result? These are equal to each other. And the result will be 4 by 4 this time, right? So as you can see, exactly. So as you can see, let's do that. The A times B is not equal to B times A. And most of the time you cannot even multiply it. Make sure that the sizes match each other to be able to do these calculations. Okay? So this is what I wanted to tell you. And can you add these two matrices, A and B? Can I do this calculation? A plus B? To be able to do that, both matrices should have the same size. You cannot add these because matrix dimensions must agree. Okay? You can add these because it will add element-wise. So the sizes should be the same to be able to add two matrices. And Said Demiral has some, let me. Okay. If I multiply a matrix with some constant, this will increase, this will double the elements of A. What was our A? Let me remind you A first. A was that, and if I say 2 times A, it will double the elements of each in row and column. 4, 10, 12, minus 2. It will multiply by 2 for each entry inside the matrix. And in MATLAB, this is not logically true in as a mathematical calculation, but you can add 3 in each element by doing this. So if I say a matrix plus 3, it will add 3 in each entry inside the matrix. Okay, this is just one function in MATLAB. And also, if you are multiplying two matrices, let's say B times B. Let me remind you B first. B was that. But let me define a square one, C. I will define another one, C. And C is 2, 3, 6, 1, 5, 8. I don't know. I am just writing one couple numbers. So 3 by 3. And if you do C times C, you will get this result. But if you do C dot times C, you will get that result. What is the difference of this and that? If this is your C, look at that. You can see what does C dot is doing. It is doing element-wise multiplication. It is multiplying 2 by 2, 3 by 3, 6 by 6, 8 by 8, 5 by 5. So it is doing each element with each element. So first column, first row is going to be multiplied with the second, first column, first row. So you can do this by adding dot before the multiplication. This is going to make your vector or the matrix as the data points, element-wise. Okay? But for that one, this is going to make the normal matrix multiplication by row times the column, row times the column. This is the difference between dot and not dot. And for example, for our B1, can I say B square? No, because I cannot multiply 4 by 3 with 4 by 3. The sizes does not match. But I can do dot, right? What do I mean? You can understand with this example. Look at that. If I do B square, which means that B times B, what will it be? This is 4 by 3 and another B is 4 by 3. Can I multiply 4 by 3 with 4 by 3? No, the size does not match. As you can see, once I try it, it says that no, incorrect dimensions. You cannot do that. But what you can do dot square. And in this time, it will multiply with first element of this one with the first element of the second. Second with second. Third with third. Fourth with fourth. Element-wise, this is what I mean element-wise. Is it clear? Like A1. Okay, that's good. So to be able to do that, you need to put these dots before power, right? Before power, before dimension, before multiplication. So it changes your calculations totally, okay? Adding this dot, just one dot, makes a difference. And you can define an identity matrix, some, already defined built-in matrices in MATLAB, like I. If you do I2, it will be a unit matrix with 2 by 2, identity matrix with 2 by 2. And, I3, I5, you can define I20 even, I'd say. It will be an identity matrix, but it doesn't, of course, looking good in that one. So this will be an identity matrix. And you know that for the identity matrix, we are using to be able to find the inverse of a matrix. Because the inverse, what was the inverse means? You have one matrix A, and if you multiply this matrix with the inverse, you will get identity matrix, right? So this is what you know it, and either you multiply it from right or from left, you should get the identity matrix to be able to say that A has an inverse. And we are using an identity matrix at that time. And for the inverse, you can find the inverse of any matrix by INV command. INV of, it was C, right? I have a square because it has to be a square, you know that, to be able to get the inverse. Yes. And you can find the inverse of your matrix by inv command. And of course, not all square matrices have inverses. For example, let's define one matrix. It all has 4 by 4 ones. Does this matrix have an inverse? It's a very simple matrix. And it says that matrix is singular to working precision. So it doesn't have an inverse, which means that it is singular. We will remember what was singular mean a little bit later, okay? So determinant is 0, right? If it is singular. And to be able to check the determinants, you can check by that command. See, it is 0. As long as your determinant is 0, your matrix is singular and you cannot find the inverse of this matrix. And this is good, which means that if you have a system that you want to solve, you cannot have that solution that you are looking for. That's why we don't want singular matrices. We want matrices that can invertible. And for the C1, you can see the determinant of C is not 0. It is negative 121. And you can, as I told you, find the size of matrices, you can find the determinant, you can find the maximum element of any matrix by maxi of each row. See where was that C? Let me remind you, C. Here you go. It will be the maximum of each column. So the maximum of this column is 8, this column is 8, this column is 8, okay? And you can find the minimum of each column in the same way, like that. The minimum of this column is 1, this is 3, this is 1. This can be handy for your calculations. You can find the sum of each column by sum command. So it will be adding these elements and giving you the result. You can find the average of each column by the mean. So these kind of things, you can find the diagonal of your matrix by diagonal C. You know that 2, 5, 1, and it is giving you 2, 5, 1. And this kind of things, you can do it in MATLAB easily. And to be able to find the system, let's say that, let me open that one again. Let me define a system. Let's say we have x plus 2y plus 3z equals 4 and 5x linear system. You remember it from the linear algebra. 7z equals 8, 9x plus 10y plus 11z equals 12, let's say. Okay, you can, you don't have to define all those in computer. You cannot define these functions in computer. What you need to do is you need to turn this one into a data. And these data, what we call these matrices. And for the coefficients of each x, y, z, this is x variables, this is y variables, this is z variables, you can define this system into a computer like with the coefficients. 5, 6, 7, 9, 10, 11, right? And let's say this is our A matrix. And you can define the right-hand side constants as B vector, like that. And with this A and B, you can do the calculations you want to be doing with this system. And this is much more handy and easier. And you can define all those in the computer like that. And one of this was coefficient matrix. And we were doing, if you remember, the Gaussian elimination. Oops, let me do like that. By defining the augmented matrix, and the augmented matrix was the same one, but you are putting the right-hand side inside your matrix. This is augmented matrix. So this is the coefficient, this is the right-hand side constant, right? So you can define these inside your MATLAB. Let's define A inside the MATLAB, which is 1, 2, 3. Something else, it doesn't have to be the same. Minus 2, 3. I don't want to turn back to that one and check it each time. 12 and 0, 2, 0, 2, 10. What's 10? And as you remember, if I put semicolon, I will not see the output, but A is still attached to this matrix. And let's define B. I don't want it messy working space. That's why you can use semicolon to be able to hide the output. And B is column vector because I put transpose there, right? And now you know that if you have a system like that, let me open that one. What kind of system we have here? A times, let's say, X, big X, equals B. A is this matrix, B is this matrix, and X is X, Y, Z. This is the capital X, let's say. Okay, and this is. So what we have, A matrix times this X equals B. And how can I find this X? Normally, divide each part with A, you will find. No, in matrices, we will not do that. We are multiplying each side by A inverse from the same place. Sorry, it's not like that. Where are you? Here you go. Then you can find, since A inverse times A is an identity, here identity, you have X equals A inverse B. You cannot see? I am sharing. No, I'm not coding. I'm just writing inside this one. And the coding part is not open right now. I'm just showing you how we can find the solution that we are looking for, X, Y, Z. Because writing this system is we are trying to find the best X, Y, Z that fits all these three equations. And solving the linear equation system means that I'm trying to find this X, Y, Z. And to be able to solve the systems in linear algebra, you remember it was A inverse times B. And in MATLAB, what we are doing now, I opened the MATLAB part. You can do it. X equals A. The division in MATLAB is the, opposite division, not like that. If you use this sign, you can find the result. And this is exactly the same as inverse of A times B. You can see this is gonna be giving the same result. So to be able to find the solution of a system, what you need to do is define A matrix, define B, and use this back division. And this is gonna give you the result of the solution of your system. And we don't prefer to use inverse in our calculations. We only use this one for theory because it will bring lots of error into the system. Since we are looking for AX equals B, you can see the, did I define as? Yes. A dot X minus B, so that AX is equal to B. So to be able to see your error, you can check the difference between AX and B because we are looking for they should be the same. Okay. So let me define different matrices, like A is equals to ones. It will, as you remember, if I do that, it was giving me, oh, this is a singular matrix, don't do that. And let's define a random. If you put rand command, it will define a matrix that you specify the length, let's say 4 by 1, between 0 and 1. If you put rand and it will be any number. That's why I'm defining a random matrix that can have any number 4 by 1. And if I say the solution of this one, let's say this is my matrix, this is my right-hand side, and what will be the solution of this system? If I do that, it says, no, matrix is singular. You cannot do that. There is no solution. Because of the matrix A, it is so simple. It only has ones as the entries. And this is going to give us a matrix not invertible. Determinant is 0. Okay? And this can have lots of solution. So make sure that check the determinants of your matrices before you the solution. If it is 0, you cannot make this is not going to make you a good data values. Change your experiment, change your parameters, and make sure that you get a good one as a matrix. It's not a number, and the other one is infinity, which means that it cannot find a solution, because you know that once we are doing a math with the computer, it is doing all numerical solutions. So all the numerical methods we are talking about, these are the kind of the idea behind the behind these functions. Okay, so if it cannot find, if it cannot reach the solution, it will tell you either not a number or infinity. Okay, and this means that it's not a good result. Okay. So you know the basic theory, I will not repeat to you. We already talked about them. You know, the equation has exactly one solution if determinant is not 0. If A has an inverse, this is what I have been telling to you. And the only solution AX equals 0 is X equals 0. So this is also, these are all equivalent things. The columns of A are linearly independent. The rows of A are linearly independent. This is what we talked about in linear algebra. I'm just reminding you in here. If the equation has 0 or infinitely many solutions, then determinant is 0. A does not have an inverse. So once you have the data, and if you have this kind of system you should solve, make sure that check these either determinant or if A has an inverse, and they will be all going to the same end. Okay. And let me read this one to you. Linear systems of equations naturally occur in many places in engineering, like structural analysis, dynamics, or electric circuits. Computers have made it possible to quickly and accurately solve larger and larger systems of equations. Because in here, since as an example, we are talking about very small sizes. But in general, once you load the data that it came from, I don't know, the companies or the results of your experiments, the data will be so big. So working with that data is not going to be that easy. We are just showing some examples with small ones, okay? So not only has this allowed engineers to handle more and more complex problems where linear systems naturally occur, but also prompted engineers to use linear systems to solve problems where they don't naturally occur, such as thermodynamics, internal stress-strain analysis, fluids, or chemical processes. So it really became a standard practice in many areas to analyze a problem by transforming it into a linear systems of equations, because you need computers. You need to define these systems into computers. So that's why you need matrices and you need linear algebra. Okay. And here you go. As I was telling you, this is one system. You can define this system into a matrices with some coefficient matrix, some unknowns, and some right-hand side. And this is your augmented matrices. And by defining this A and B into a computer with the opposite division, you can find what is x1, x2, x3 easily. Okay, but what is happening behind it is Gaussian elimination. You remember that, right? So it was our first pivot element. We were making that elements behind it 0 by multiplying the first row with -2 and add to the second one and make this entry 0. And once you come to the next one, the first non-zero element is the pivot. And this is our pivot. And you need to make the elements under it, it's 0. So to be able to make this one 0, multiply the second row by 2 and add to the third one. And this is what you will get. Once it is triangular matrix, you can easily find the solution by back substitution, which means that if this is x, y, z, 2z equals 4, then z equals 2. If z is 2, you plugged in here, find y. And once you find y, plugged in this one, because this is x minus 2y plus 3z equals 4, you found z, you found y, you can find x. This is the back substitution, right? And you can find it easily. And for this kind of augmented matrices, most of the time there will be lots of zeros, and this is what we call a sparse matrix, okay? And for the applications in general, you will have this kind of matrices. And in these ones, you don't want to spend your time with lots of zeros. You want to focus on the ones that is non-zero entries, and there will be different methods to be able to do that. But now let's remember the triangular matrices and the back substitution. As I told you here, you can find Z or X3, they called it X3, X2 and X1 easily once you have this triangular matrix, right? And we will be doing this. How can we define a program? If we give a triangular matrix, it will give us the back substitution and the result. Let's do that with MATLAB for you to get used to the MATLAB and the coding part. I will open a new script. And in this new script, I will define a function. And in this function, it will do back substitution and it will give me the result of my system, solution of my system. Back substitution, back sub I call it. And I will give a triangular matrix A and the right-hand side constant B. This is what I will give to the as an input to my function, and the output will be the X solutions. Okay. Now in the body of my function, I have to define output in terms of inputs, right? So I have to know, since these are gonna be defined for any size, I have to know what is the length of any of it so that I will do for loop in that size. Length of B is gonna give the how many elements does this B has, sorry. And after that, I will define my solution firstly as a zeros matrix with n by 1, because this is how what is the size of my solution. First I will define as zeros, and after that I will update this X solution matrix. And the last one, the last entry, we know it, the last entry is the last entry in B over the last entry in A. Sorry, this is not the opposite, it is the normal division, that one. Because the other division was matrix division, but in here I will just take two entries, two values, and I will just divide them. And once I have this starting point, I will start. So let me show it to you. Firstly, what I did, I took the last entry in B, which is the last entry in B, 4, over the last entry in A and N, A3, 2. 4 over 2, 2. So this is how I will start. Once I have this 2, I will put this one inside here, and I will find x2, right? That's why I started my program by dividing the last entry of B with the last entry of the matrix. And now I will do my for loop. Oops, what did I do? For I or K, it doesn't matter what you say. Let's say K equals n minus 1. Since I used already n, I will start n minus 1, and I will go backwards until the first entry. So I already defined the third one. I will be doing n minus 1, which is 2, and I will go until the 1, the first one, right? That's why my for loop starts with n minus 1, and it is gonna be going to back substitution, as we say. The solution x, so this is capital, I define it like that, K will be, now how can we define that? This is the important part. So this will be K, whatever the K. If n minus 1, it will be n minus 1. Because look at that. It will be 7 minus 6 times n minus that one. And this is I'm trying to define. So BK, whatever the K is, minus A plus 1 till, sorry, this K is gonna be small, till n times x K plus 1. Again, you don't have to code in that way, but I want you to understand just the logic behind and how you can call this program and how you can work this program. Okay? I hope I did it right. So once you write your function program, this is I want you to know, you need to save this one. Let's save that one. I save this one as desktop, my 300 course backup. Okay, let me save that. Once I save it, I cannot run the function program. I need to call it from the console with the inputs that is needed. In here, what I need A and I need B. So I need to give A and B, and with this back substitution, I can find the solution. So let me define this A. A is, what was that? Once I define those, I can easily call this program 1 minus 2, 3, and 0, negative 1, 6, and the third row 0, 0, 2. Okay, I define my A matrix. I will define by my B 4, 7, 4. And now I have to call my program. I want X. That is box substitution A and B. I already defined. Uh-oh. Why it is not working? Can you tell me? Look at in here. Because my directory is showing bin. And in bin there is no backstop program. It says backstop is not found in the current folder. That's why I need to change my folder, because my program that I wrote, I put it inside this one. Now I can call it again and it will give me the result as 852. Let's see, is it true? Is the result 852? Yes, it is 852. So this is the program that once you define the triangular matrix with the right hand side, it will give you the solution. And you can check one by one how the program is working behind. But again, you don't have to understand that part at least, but you need to know, once you have the function, how can you call it? How can you define these inputs? Because maybe these are not specific for you, but in the future you will need some functions and you will Google it at the beginning. And once you have the ready program, you can easily update these programs according to your own problem. To be able to do that, you need to know at least some part of this MATLAB. Okay. And this is our back substitution program. I will give you the whole program that can do the Gaussian elimination. But we don't have to. Again, do I have it in my hand? I will check it a little bit later. I will send it to you anyways in LMS. So after this point, I want to point out the things about the LU decomposition. Okay. Let's give a couple minutes. I will check this program and we will continue after that. Okay. So 5 minutes break. We will start after 5 minutes. Okay, let's continue. So we talked about the back substitution, and now I will be pointing out some accuracy condition numbers and pivoting terminology. Let me see. So what you can, or the program is going to do rounding, or you can do rounding, and this effect of rounding sometimes can make you a wrong solution. And to be able to show that, I want to give you this example. Let's say that our computer can only, of course it's not true, but only store 2 significant digits, and it is asked to do Gaussian elimination for this system. But it can only store 2 significant digits. Then doing this elimination, how can you do that? You need to cancel this 1. So if you multiply the first one by minus 1000 and add to the second one, if you do that, this is going to be 0, minus 1000 plus 2, minus 998, 3000, minus 3000 plus 5, it will be this number, negative 2995, right? So if you have this with the back substitution, you can find x and y. So, but since the computer is gonna round 2 digits, it would store this matrix as 1, negative 1003, negative 3000. And you can see that, okay, these are so, close numbers. So what? And if the back substitution is done, it will give you the result. X2, it will be here 3. If x2 is 3, x1 will be 0, right? This will be the solution. But if it doesn't round to 2 digits, for the unrounded system, check that out. What will be the x and y? X2 will be 3.001, and if x2 is 3.001, x1 will be 1. As you can see, for the rounded one, it is 0 and 3, and for the non-rounded one, x1 is negative 1. So totally different results. So this kind of errors you can get if you are rounding your numbers, and if you are specifically work with the small numbers, like lots of decimals, okay? And to be able to get rid of this kind of error, what you can do is the pivoting. So for pivoting, what you need to do, you need to switch rows that has the biggest, as an absolute value, biggest value to the top. Look at the column. If this has the biggest absolute value, move this one to the first one. You know that for row operations, the solution is not going to change. And so that you can get rid of the all kind of errors that can done with the rounding. Okay. So pivoting is crucial. For example, for that one, look at the first column. There is nothing to, change. For the second one, don't look at the first row. 1 and negative 2. So what you need to do is you need to change the third row by the second one. And so that after pivoting, this is what you will get. And for this kind of systems, you will see less error because of this kind of rounding and other issues. Okay. So in system, we are applying pivoting first. We are moving the highest weighted element into the upper row. Okay. And condition number is telling us what kind of matrix we have. Problems occur without rounding. And here we have the same A, look at that, but 2 different inputs. 1, 1 over 2, 1 over 2, 1 over 3. So our A matrices are same. Look at the B ones. 3 over 2, 1, 3 over 2, 5 over 6. As you can see, the difference is 1 over 6 only. So with the same weighted A, you are giving different inputs. And you can assume that, okay, my inputs are so close to each other, and my results will be also so close, because you are changing your input little by little. If your matrix is good enough, or strong enough, or true enough, you can get a smaller result, a similar result. But look at that. Even though the inputs that we give, like the B values, are so close, the results are totally different. We don't want that. So This means that our system is not robust. If I change the input little bit, the solution is going to change a lot. We don't want that. Okay? And how we can make sure that? We can check the condition number of our matrix. And this is how the condition number of matrix is in general calculated, but you don't have to calculate that. With this command, condition A, it will tell you what will be, how is your matrix? Is it good enough or not? Okay. So let's try some condition numbers in that one. So so there are some matrices in MATLAB, predefined one like Hilbert matrix. And you can define the size of these ones. Let's define the Hilbert matrix by 2 by 2. Okay. And the condition number of this one, just if you want to work with this matrix and you want to make sure that how robust is this matrix, so 19, which means that small errors in the input, if you put any B and if you want to change the input, it can get magnified by 19 in the output. Okay, so you want this number as small as possible. And you can define different matrices. Let's define another matrix. For example, 1.2967, I don't know, 0.832. Let's go to the other one, 0.2167 and 0.1142. Let's say this one. And let's look at the condition number of this matrix. It is 63 times bigger. So it is also worse. Okay? And let's find the determinant. What is this matrix? It is really condition number. Okay, let me define another one. I think this is better. I will copy paste from there because it's harder. I want to show you this one because this has really big condition number. And look at that. Look at the 10 to the 8. So if you change your input little bit, the difference in the output can reach to 10 to the 8th, difference. And this is what we don't want. And you can check the determinant of this matrix. And you will see that it is so close to the 0. Even though it is not 0, it is close to the 0. And you know that we don't want that because it will give us a singular matrix that we cannot work well. So if your condition number is so high, you can also understand that your determinant is very close to the 0, which means that your system is not robust. Don't work with that. Okay? These are a couple concepts I want you to know. And I also provide you in the class notes the function here for any Gaussian elimination. And to be able to work this function, open a new script, copy paste that one, and don't forget to copy paste the remaining. I put it in 2 different. Okay. As I told you, what I want from you is make sure that you know how to work with them. Okay. And you cannot run. You need to save this one. I will save this one again in Mat 300 upper triangular. Okay, VK. Let's do that. And now I need to define A and B. Let's define A and B. My A is 2, 4, -1, 5, -4, -5, 3, -8, 2, -5. This is my third row. -4, 1, and my last row, negative 6, 0, 7, minus 3. Okay, let's say this is my A. And my B, so it is defined, it doesn't matter actually, if you don't have to give the same name even. Negative 2, 1, 8, 1. And of course it has to be column. Let me open for you to see. And let's call this function. And as long as, since I define my function with the same name I have to define, and it is in this folder, so I can easily call this function. Once I define A and B in the comment window, I will just copy paste this part in there and I can call it, and as you can see, the solution is 0, 0, 0. 0 solution for X, Y, Z, or X1, X2, X3, and X4. Okay? So you can easily find if A is n by n non-singular matrix, B is n by 1 matrix, the output is the solution. Okay? And first we are initializing our solution in here, and after that we are doing the Gaussian elimination in here. It's very close what MATLAB is doing once we use A back B. Okay, oops, it's not that. And as you can see, it is so close, so big, and it says that matrix is close to the singular or badly scaled. Results may be incorrect because the condition number, look at that, it is 10 to the negative 18. It's also, we want close to the 0. Okay. So we will talk about the LU decomposition and the two Gaussian, two iteration methods, Gauss-Seidel and the Jacob iteration next week. And let me open the, where is that? It's 100? Oh no, this is that one. Here you go. So after the Jacobian iteration, we have our examples and quiz 2. So we have, next week we have the quiz 1. Okay. After that, we will talk with the linear algebra part 1 more week. And after that, we will start the curve fitting and interpolation according to our syllabus. So do you have any question so far? Let me close share. Okay. Okay, I will share again the notes and the recorded class with you. Make sure that next week you have your first quiz. So work with the lecture notes I gave it to you and work to your homework problems, and you will be good in that. Okay? And if you will have any question, you can ask to me. Again, if you don't have MATLAB, you can work with Octave. If you cannot download it. I don't know how many questions. I still did not prepare. Once I prepared, I will tell you, okay? I will send you an email and tell you. Yes, you will. You need to use MATLAB in the quiz or Octave. Okay. Okay, then see you next week. I'm stop recording.